Thank you very much, Konstantin, for the introduction, and thanks a lot, the organizers, for the invitation. In the talks by Maxime and Hiroshi, they already mentioned the F-bundles and the blow-ups. In my talk, I hope to provide some more explicit formulas, and hopefully we can actually do some calculations for specific examples. And also, I hope that they will help us really understand what exactly the blow-up formula is. And it's joint work with Ludmila, Maxime, and Tony Party. So I will start just by reviewing, set up the notations for Gromov-Witten invariants, and reviewing again F-bundles. Then I will quickly go through the heuristics from homological mirror symmetry, which suggests this blow-up formula. And then we will look at F-bundles at the limiting point. And in order to do the decomposition of F-bundles at the limiting point, we will do some calculations using universal algebra. And this universal algebra calculations suggest us some explicit formula for decomposition of the F-bundles. And eventually, this allows us to prove the existence of gauge transformation at this limiting point. And finally, the idea is to use so-called theorem of extension of framing for F-bundles in order to get this decomposition formula from the limiting point to the whole formal neighborhood of this base of the F-bundle. So this is a rough plan. Yeah, so I will go quickly for the just the basic stories. We have a smooth projective variety X over complex numbers, and we count algebraic curves inside X. So we have this famous problem about counting rational curves in D2 of degree D, passing through 3D minus 1 points. In general position, we get these interesting numbers. They are all computed by Konisevich recursive formula like this. So the main question for this talk is that when we have a blow up X tilde, which is blow up of smooth subvariety Z inside smooth projective variety X, how can we count curves? How can the curve counts for X tilde be computed in terms of curve counts for X and Z? So we already seen in the talk by Hiroshi that we have this very beautiful, or maybe he will talk about later in his talks, very beautiful decomposition formula. And also there have been a lot of works in either like under some assumptions or special cases by Y.P. Lee, his student Honglu Ban, and their collaborators. Yeah. So yeah. Okay. So of course we need to be a bit more precise because of troubles of naive curve counting. So then we'd better formulate this problem in terms of Gromov-Witten theory. So we introduce this space of stable maps, and inside we have virtual fundamental class. And we restrict to genus equals 0, and this gives us rational Gromov-Witten invariants, which are just defined as a pullback by evaluation map of this cohomology classes, and we integrate over virtual fundamental class. So in particular, for Gromov-Witten invariance, we have this WDVV equation. We can explain it like this, write it like this. So it follows from this identity between, like for the curve counts, when we change the cross ratio of the domain curve, and we get an equality for when we take sums of all these counts. When we switch phi2 and phi3, for the observables, we get equality. And this is a generalization of Konsevich's recursive formula that I mentioned in the very beginning for these numbers. And from this Gromov-Witten invariance, we build this Gromov-Witten potential that also in Maxim's talk. And this Gromov-Witten potential, here we treat it as, we consider this Gromov-Witten potential as a formal series in this ring. So the Gromov-Witten numbers are rational numbers. And here we have q to the power beta. This is lives inside the formal completion of this group ring or monoid ring associated to this monoid of curves. And we also have all these formal variables Ti that keep track of these observables. So yes, so these Ti, they are the basis of cohomology. I wrote it here. The T lower I, T upper I, they are due basis of this cohomology of X with rational coefficients. And the little Ti are the formal variables to keep track of all these observables. So these are, we have this Gromov-Witten potential. And from this Gromov-Witten potential, we make this quantum product by taking third derivative of the Gromov-Witten potential. And this WDVV equation that I mentioned above gives exactly the associativity of this quantum product. So now we can reformulate the main question for our talk. When we have smooth projective variety X and a smooth subvariety Z in closed subvariety Z inside X, we have X tilde the blow up. So we want to relate the curve counts for X. So how can the curve counts for X tilde be computed in terms of curve counts for X and Z? So now the question becomes, how can the Gromov-Witten potential for X tilde be computed in terms of the Gromov-Witten potential for X and Z? Okay. In order to answer this question, it's kind of how do we relate these two power series? So in order to answer this question, we introduce this notion of F bundle that already appeared in Maxim's lecture. Here, I have maybe a bit more precise formulas. Yeah, so because before the question is really about how to relate these two formal power series. And it's not that easy to see what do we do, what operations we can do on this formal power series so that we can convert one into another. And in order to do that, we need some further packaging of Gromov-Witten invariance into differential geometric data. And this is what F bundles are about. So the precursors of F bundles there are many, and all of them are like quite similar. We have Frobenius manifolds, F manifolds, TE structures, cytostructures, non-commutative Hodge structures, all these different variants. Here we introduce the definition of F bundle. It's almost exactly the same as TE structure, or this what's called a quantum D module in Hiroshi's papers. Here, I think originally we called it F bundle because we wanted it to be both have the meaning of Frobenius and formal. But later we realized that we need to work with non-Archimedean also. So then, strictly speaking, F bundle is really, if you know the definition of all these older structures, then F bundle for the non-Archimedean case is exactly the non-Archimedean analog of this TE structure in the complex case. I think initially we wanted the U direction to be formal, but now for the, if we go to the non-Archimedean analytic case, we can also allow the U direction to be analytic. Okay. So the reason we consider the base to be formal scheme or non-Archimedean analytic space is because we don't really know about complex analytic convergence for the Gromov-Witten potential in the general case. And here, the blow-up formula is supposed to work for any smooth projective variety. So we have to use this non-Archimedean or formal setting. Okay. Here we let B be a formal disk, either a formal disk that is K double bracket U or a germ of K analytic disk with coordinate U. Yeah. Then an F bundle over B is just a pair curly H nabla, where H is a vector bundle over this base B times this disk. So this extra U direction. In the formal case, it's formal disk, and in the analytic case, it's germ of analytic disk. And then we have a meromorphic flat connection on H, nabla a meromorphic flat connection on H with poles at most at U equals 0, such that, so roughly speaking, we want second order poles at 0 and first order. Yeah, we want second order pole at 0 in the U direction, and the first order pole in the B direction. So in other words, we want that when we consider the connection in the direction U squared du and the connection in the direction U psi for any vector field psi, we get regular. So second order pole in U direction, first order pole in the B direction. And this is the definition. Any questions? Okay. Okay. So here is the A model F bundle from Gromov-Witten invariance. Yeah, here I wrote down the simplest formal base, which is we have these formal variables for curve classes and the formal variables in the T direction. And then the curly H is just a trivial bundle with fiber given by the cohomology. It's better to consider the non-Archimedean version of this, which is already appeared in Maxim's talk. He explained that for this direction, we are taking pre-image of the ample cone, And for that direction, we are taking analytic polydisks, open unit polydisks. Then we have quantum operators, KGA. So K is this canonical bundle, a canonical class plus this combinations of basis Di, and we take quantum multiplication with all this. And G is the grading operator, and the A is Ti, quantum multiplication by Ti. Then we have formula for the quantum connection. In the U direction, it's given by this. In the Ti direction, the T directions and Q directions. So we have this quantum connection in 3 directions, U, Ti, and the Q. And this gives us the F bundle, the A from the A model connect, A model F bundle for a smooth projective variety. And the flatness of this connection is exactly follows from the associativity of the quantum product, which is from the WDB. Okay, so far it's just a review of notations, and when we have mirror symmetry, we have we know from mirror symmetry that the same thing, same notion F bundle should also appear on the B side. We have a B model F bundle that are constructed from Gauss-Manuel connections. Okay. So once we introduce the F bundle, we can reformulate the main question for this talk. We have blow up X tilde of smooth projective variety X along a smooth center Z. And we want to relate the curve counts for X tilde with the curve counts for X and Z. So we put all the curve counts, package them into generating series. And now we want to relate the Gromov-Witten potential for X tilde in terms of Gromov-Witten potential for X and Z. And we have further put the Gromov-Witten potential into F bundle. So now the question is, how can we relate the A model F bundle for X tilde? How can the A model F bundle for X tilde be computed in terms of the A model F bundles for X and Z? Yes. So and now let me just quickly go through the heuristics of homological mirror symmetry, which gives us suggests this decomposition formula. So mirror symmetry is a conjectural duality between Calabi-Yau varieties. When we have a Calabi-Yau variety X, it's conjectured we have some mirror variety X check of same dimension, and then we have a lot of relations between X and X check. So the simplest one is we have a Hodge number correspondence, HPQ of X is equal to H dimension X minus PQ of X check. And then we have the Hodge theoretical mirror symmetry. So now we can just state it very clearly using this notion of F bundle. We can say that the A model F bundle for X is equivalent to the B model F bundle for X check. And of course, if we add more structure, like the lattice structure, we also get, if we incorporate the Q structures, we obtain this so-called NC Hodge structures, and it gives us conjectural relation that A model NC Hodge structure for X is equivalent to B model and see how the structure for X check. And for all these, all these conjectures in the toric case, I think are in papers by Hiroshi Iritani and his collaborators, and maybe also for completed intersection. Some of them. Some partial, yes. So the further generalization is homological mirror symmetry. We get this equivalence between Fuqua category and the dB of the mirror. Here, when we consider blow up of general variety, we also consider this mirror symmetry beyond the Calabi-Yau case, where we have, let's say, X final variety, and we choose a point little b in the base of our F bundle, and the mirror will be a Landau Ginzburg model, which is a variety, smooth variety Y with a potential W, such that the critical locus of W is proper. And then we have correspondences between the eigenvalues of the quantum operator K for X and the critical values of W. And this also gives we also get the equivalence between the F bundles. So we have A model F bundle for X is equivalent to B model F bundle of YW. I don't know how to do the other direction. So for the Fuqua category, in order to do it for a general variety that is not a Calabi-Yau, we consider Fuqua category conjecturally for a given eigenvalue C, and this is supposed to be equivalent to the matrix factorization category of Y with the potential W minus C. And also, if we consider, we can switch the role between A model and B model. And when we consider the dB of X is supposed to be equivalent to the Fuqua-Saito category of YW. And from here, we see that this Fuqua-Saito category admits, by the construction of this Fuqua-Saito category, this admits a natural semi-orthogonal decomposition with respect to these eigenvalues. And this semi-orthogonal decomposition of the Fuqua-Saito category suggests a semi-orthogonal decomposition of dB, and which further suggests the decomposition of Hodge structure of X. And this is what Maxime was trying to explain in terms of this decomposition into atoms. And on the other hand, if we consider this Hodge theoretic picture, then the decomposition of B model F bundle for YW suggests decomposition of A model F bundle for X. And if we go back to the blow-up case, we have X tilde, that is blow-up of X along the center Z, and apply the blow-up map. And we choose a limiting point, little b, corresponding to pi upper star omega for some ample plus omega on X. Then we can compute the eigenvalues of this quantum operator K at this limiting point. When we try to compute this eigenvalue, we only need to compute the Gromov-Witten invariants that are vertical curves, curves that project to a point under this map, and that's not hard to compute. From this computation, we can see that the eigenvalues of this quantum operator K at this block, at this limiting point, consists of 0 and then some roots of unity. and which are by mirror symmetry exactly equal to critical values of the Landau-Günzburg model for this X tilde, if it exists. Okay. And furthermore, if we consider the eigenspaces for these eigenvalues correspond to, so for the eigenvalue 0 corresponds to homology of X, and all the other points corresponds to homology of Z. And this suggests a decomposition of the A model F bundle of X tilde into external sums of A model F bundles of X and the codimension Z minus 1 copies of the A model F bundle of Z. Any questions? Okay, so I hope this gives motivation for Hiroshi's decomposition theorem. And we have Iritani's decomposition theorem, saying that we have there exists a formal invertible map between the bases of F bundles, such that we have this conjectural decomposition above. Yeah. As far as I understand, at least as written as Hiroshi's paper, that this map is not that explicit in the construction. So we will hear the ideal proof in Hiroshi's talk. And as far as I understand from Hiroshi's paper is that this formal invertible map is not explicit. And also, I think you wrote that you didn't think about it. So the uniqueness is also not very clear. So therefore, it's not really, we can't really use it to actually compute things. And we can compute, you know what happens. I think it's fine at least. It's okay. How do I go? Okay. Yeah. So we yeah. So since this map is not explicit and also uniqueness is not clear, it cannot really be used to compute the A model F bundle for X tilde in terms of A model F bundles for X and Z, and give an answer to our original question. And but even, I mean, maybe you think you don't really care about the original question, but even also for the question we want about atoms, in order to get for this atoms and the application to birational geometry to work, we want a canonical identification for this block formula. Yeah. So now let me try to describe a more explicit way to obtain this decomposition. Okay. Let me see how to get rid of this zoom. Just share my screen again. Okay, can't get rid of it. Or maybe it's because I think I have to do it there. Okay. I give up. Okay, let me give a more explicit way of for obtaining this decomposition. Yes. So first, let's look at what are the F bundles at this limiting point. Here is our setup. We have X smooth projective and Z smooth closed subvariety embedded in X. And we take blow up X tilde over get X tilde mapping to X. And E is our exceptional divisor. Then D is dimension of X. We have M codimension. Let M be the codimension of Z. And N is the normal bundle. E is the exceptional divisor. H is O1 for E. Then we have the splitting isomorphism of cohomology groups. So we denote by H split the direct sum of HX with shifted direct sum of shifts of copies of the cohomology of Z. And then we have an isomorphism between this direct sum with the cohomology of X tilde. It is in Claire Voisin's book. And then with respect to this isomorphism, we can calculate let's calculate the quantum operator K limit on this cohomology of X tilde at this limiting point above with respect to this splitting isomorphism. So if we calculate it carefully, we get this block matrix it's in matrix form with respect to this direct sum. And now, since our goal is to get a decomposition formula for the F bundle for X tilde, and we have this K at this limiting point. So the question is, how can we diagonalize? The first question is, what can we do to diagonalize this matrix X, this K limit, this matrix at this limiting point? So if we look at this matrix, most of them are just multiplication by characteristic classes, but we have this like lower star, upper star, which are a bit cumbersome to work with. If you want to just treat it as a matrix. Yes. So in order to really work out the diagonalization, like to really study this matrix, the idea is first to kind of get rid of this lower star and upper star. So for this, we consider the following universal algebra calculations. Let X be the degree operator on the cohomology of X, so we need this degree operator because in this quantum connection, we have this term, this grading operator. So we consider degree operator on HX. So that is the degree operator acting on the cohomology class of degree I. It's just the multiplication by I. And then we have degree operator in the Z direction for Z. Okay. And now we consider two rings, one for X, one for Z. For X, we have Q, we put the degree operator, and we also put formal power series in C1 of Px, here consider as just a formal variable. And then we have, we consider R2, which is the ring, Q with this degree operator deck Z, together with C1 of TZ, C1 of N, until Cm of N, all considered as formal variables. So unfortunately, these rings are not really commutative. They have a little bit of non-commutativity because of this degree operator. So we have the following commutation relations. And this K-limit we had before. This K-limit we had before is now after we set up all these abstract rings. The K-limit we had before is an element of this universal algebra written in this block matrix form. And it maps to the endomorphism of the cohomology of X tilde because all of them can just act on the cohomology of X tilde. And so now we have embedded our particular matrix into this algebra. And in order to get rid of all these lower star and upper star, in order to facilitate computations in the universal algebra, we consider the following embedding of algebras. So we embed this universal algebra A that is given by block diagonal matrix of this form into this ring that is into this ring that is R1 direct sum of m times m matrices with entries in R2. And given by this formula, so we have this element in the universal algebra, and we put this alpha, just alpha here in R1, and then we take Cm of n times A. A is this A here. Here we have upper sigma upper star times A times. So we first apply sigma upper star, then we multiply by A, and then we apply sigma lower star. And our goal is to get this sigma upper star and lower star. So we have A, we take out A here, and we multiply by Cm of n. And also, we get rid of this lower star, sigma lower star here by multiplying all this Bj by Cm of n. And we get rid of this upper star here by doing this, and we keep all these B's. And then one can show that this tricky map, there's also a iota here. So I have alpha here, and then there's also a iota alpha. It's given by the following homomorphism. So it sends R1 to R2, dec X to dec Z, and the C1 TX to C1 TZ plus C1N. Yes. So then the observation is that after doing this tricky map, it actually is an embedding of algebras. Yes. So once we can embed our limiting matrix it was a limiting operator, not really a matrix. Now it is eventually a matrix, and we can write it in a better form. So if we just denote, there are too many term classes. Let's just denote C1 TZ by little t and CIN by little ci. And then now we can rewrite L limit as some diagonal matrix plus m minus 1 times another matrix m. Under this, we rewrite this under this embedding, universal algebra embedding, and this m has this very simple form, which is just 0 minus 1 over 1, and the Cm minus 1 minus Cm minus 1, and Cm minus 2 and minus C1. And now we can diagonalize this matrix. So the characteristic polynomial of M is given by lambda M plus this sum of Cm minus I lambda I plus lambda. So we let lambda I be the eigenvalues, and the eigenvalues lambda 1, lambda 2 to lambda n. If we model out all these term classes, now they are just the formal variables. If we model out C1 to Cm, we get exactly these eigenvalues that we computed before for this quantum operator, these eigenvalues. And it's just this, like a rotation for the testing the Wilson unit. Any questions? Or maybe I didn't introduce LLIM. LLIM should just be KLIM under the embedding of universal algebra. Thank you very much. It's just the usual K operator. Yes. Yes. So I think exactly the same eigenvalues appear in irretanus, in Hiroshi's when you do the Fourier transform and then you do the stationary phase formula. You are working with it. Okay. Yes, so this is what we get for the quantum operator at this limiting point. And next, let's also consider the other operators, because we have quantum operator K and we also have gradient operator G and the other quantum multiplications by the comodular classes. So let's consider gauge transformation at the limiting point. Let lambda be a diagonal matrix with diagonal entries given by lambda 1 to lambda n. And then we introduce, first, we introduce the corresponding, K operator for the below down, for the X and Z. So the corresponding K operator for the below down is, we write it as this one, C1 Tx, C1 Tz plus C1 T, and we also put this m minus 1 times lambda. The reason we put m minus 1 times lambda is because just now when we try to diagonalize our K, we get this extra like terms. We have this lambda, and this is the shift that we have to do in order to get the decomposition formula. So here, I think in our naive consideration, we only have this shift, but in Hiroshi, you have some shift that's little bit different. Okay. And okay. Then we also have, of course, limiting operators for G, for the gradient operators, both for the limiting point for the blow up and also for the X disjoint union of Z. And recall that the quantum operator K at the limiting point is this one that we calculated. And now the theorem is that the two meromorphic connections given by this K limit, G limit, and K split, G split, they are gauge equivalent. So this is precise. We have all the matrix written down, and still it requires some work to prove the gauge equivalence. So this gives us this decomposition theorem we want at the limiting point. And next, we need to extend this decomposition beyond the limiting point. And this, we use this general theory of frames for F bundles. Okay. Let me introduce this. So let's say I have F bundle H nabla over B. A framing is another flat connection denoted as nabla framing FR on H without poles, such that in the local trivialization of this vector bundle curly H given by this connection FR, if we denote by straight H the vector space of local flat connections, then the original connection has the following form. So the following form means that we only have, when we write it as a Laurent series in U, we don't have non-negative powers of U, and also here. A priori, for our definition of F bundle, we only said that we have second order pole in the U direction and the first order pole in the precise direction. We may have terms with non-negative powers of U, but here we don't have. When we have framing, it means that we fix some trivialization so that we don't have non-negative powers of U in the expansion for the connection. So here it's for any vector field psi on B, where KG are endomorphism H valued functions on B, and A is the end H valued one from B. Okay. And we have the extension framing theorem, a framing at a given point. At a given point on this Frobenius, on the base of the F bundle, if we already have a framing at a given point, then that extends canonically and uniquely to a neighborhood. Can be a formal neighborhood or K-analytic neighborhood of B, of little b. And the proof relies on order by order computation. We had a seminar organized at the CalTech where with my students we wrote about all the details, order by order. It's quite involved. Okay. So using the extension framing, we obtain a unique explicit decomposition for a model F bundle of blow up, and hence this relation for curve counts. So let me explain how do we do it. How do we use the extension framing to get what we want? So now say that I have two framed F bundles, formal germs. I have formal germs, little b1 in b1 and little b2 in b2. And I have a maximal F bundle hi nabla I, maximal F bundle over bi, I equals 1 or 2, together with some framing. So here it's just a germ. So framing is just a trivialization of this vector bundle HI as product of base with vector space HI. Yes. Yeah, and assume that we have a isomorphism phi. Assume we have an isomorphism phi, which lies in Hom of from H2 to H1 with coefficients in K double bracket U, such that phi, when we pull back by phi of nabla 1 at B1, we get nabla 2 at B2. So that's exactly this gauge equivalence that we prove for the follow-up case. And furthermore, assume there is a map from the base B1 to B2, sending these points, and an isomorphism phi tilde from F upper, like pullback of H2 by F to H1, which restricts to this gauge equivalence that we have, such that we get the limitation between the connections. Then this map F and this gauge equivalence phi tilde can be uniquely constructed as follows. So we just let nabla 2 prime to be pullback of nabla 1 because we already know what to do at this limiting point. Then we don't know how to extend it yet. And we first do like the most naive thing, just extend by identity. And we get nabla 2 prime. And since this right thing that we know, that restricts to phi at the point, and when we pull back by this right map, then we get something that has no terms with non-negative powers of U because it's already has framing. Therefore, we can use the uniqueness of extension framing to show that there exists a unique gauge equivalence. This capital theta, which doesn't do anything on the limiting point, and which does the job to take one into another, to take one phi into the other phi tilde. And by the proof of the extension framing, this theta can be computed explicitly by recursion on the degrees, and the same for phi tilde. So finally, in order to compute this map F, we let H be a constant section of curly H2 given by a cyclic vector in H2, in this trivialization H2. And then when we consider this connection X on H, we obtain a one form. So we get a one form on B2, and this one form gives a affine structure on the base of this F bundle. So now we get the affine structure, and we have this equality between this affine structure, between the pullback of this affine structure by F and this like gauge transformation by phi tilde that we already know. And this uniquely determines the map F. So the computation that I have shown here gives us a unique map between the base of these F bundles or Frobenius manifolds for the blow up and for before the blow up.
So for this extension of framing, we need some new tokens of the recipe.
So here we are just extending the framing. Let me see. For the nilpotence, it's needed when we want to extend the framing in the Q direction.
Yeah.
And
So if we discontinue the origin.
I think you are right. Here, actually, we are extending both in the Q directions and the P directions. But we have nilpotence, right? Because at the point, it's just the usual. Maybe the statement here, I think to be precise, then for the statement, yeah, to be precise, maybe we have to consider like a log epsilon, because the Q direction, we don't have the framing with the connection is like log in variable Q. Then I think it will work. Okay. Thank you, Hiroshi, for the question. Yes. So now, from this consideration, we get a unique